Alright, silly people, here's the situation. We are in the simple harmonic oscillator, and we are going to be constructing psi 2, that is the second excited state for the harmonic oscillator. And we're going to be using this formula for it, which I've written here, but uh, secretly we're not, because actually Griffiths already took care of psi 1, and I'm going to write down what he got. Here, you got m omega over pi h bar to the 1/4 times square root of 2m omega over h bar. We got x e to the minus m omega over 2h bar x squared. And since we have psi 1, all we have to do is apply the raising operator now to this, and then we'll get psi 2. So I'll write that. Psi 2 will just be 1 over root 2 times the raising operator acting on psi 1. Um, so I'm going to write out what the raising operator actually is before we do anything. That is, the raising operator is 1 over 2h bar m omega minus I times the momentum operator plus m omega x, right? And we're going to be doing all of that pretty much manually. So 1 over root 2, we have 1 over root 2 h bar m omega from the raising operator. And then I'm going to change the momentum operator into what it actually is. So minus h bar d dx, the I times the minus I. Just made that into a minus sign. So that's that. We had a m omega x. We have this thing to the 1/4. We got this thing from psi 1 here. And then we just have the x times e to the minus m omega over 2h bar x squared. And that's it. Already we can cancel stuff out, thankfully. We can get rid of this root 2, canceling this root 2, this m with this m, this omega with this omega. And we can move that h bar there all the way up front to look like 1 over h bar times root 2. Still have this weird m omega over pi h bar to the 1/4. That's not really going to go away. And then we're just going to factor through the stuff actually. So we're going to have minus h bar d dx of x exp minus m omega over 2h bar squared, and then plus m omega x squared times exp minus m omega over 2h bar x squared. Right. That little derivative will be one where we apply the product rule. So there's going to be a bracket in here where we're going to have one term which is only dependent on the exponent, which is going to be just something on the right of that is 1, and then one term which is going to be minus x squared. So minus m omega over h bar x, all of that, and x squared, all times the exponent. And I'm actually going to save that to the end because we also have uh, m omega x squared there, all times the exponent. Right. Um, yeah, so there is a bit of a nice simplification, um, because when we factor that h bar through, we see that this thing has all the same terms as this thing, so that they'll just add up. But other than that, it doesn't get much more simple. And I'm going to factor the h bar all the way back here to the stuff inside. So we just have 1 over root 2 m omega for pi h bar 1/4. We'll have 2 m omega x squared over h bar minus 1. Cool. And all of that times the exponent stuff. All right. Griffiths also asks us to plot all of this. I have a Desmos plot to show you. So these are our wave functions that we've got here. I've written them all on the bottom screen there. The keyboard thing's actually cutting off the square root 2, but that's fine. The red one is the ground state, which I didn't explicitly write out here yet, but there it is. It's also in the textbook. You can see it just has one node. The second wave function, that is the first excited state, psi1, is here in blue. It has 2 nodes, one negative, one positive. And then the second excited state, psi2, has these 3 nodes, 2 above, 1 below. So, interesting to note, psi1 is antisymmetric about the origin, and the negative component will exactly cancel out the positive component whenever you integrate over all space. What I'm saying to you is the integral of that thing is 0. And also the integral of anything that you multiply it by will also be 0. Because, or if you're multiplying it by an even function like psi0 or psi2, then the integral will become 0. If you multiply by an odd function, you probably get something non-zero. Maybe. Remember how I just said if you multiply the first excited state wave function by any other wave function, that the integral over all space of those two multiplied things is 0? That takes care of the orthogonality condition proof for psi1 and in combination with psi0 or psi2, because those are both even wave functions. So you're multiplying an odd function by an even function and multiplying it so you get 0 either way. What is less trivial is actually just the multiplying the psi0 with psi2 and actually calculating the integral of those guys and proving that that is 0. So what that looks like, you have a couple of powers of the weird m omega over pi h bar stuff, but now with a root 2 on the bottom as well because of the second excited states form that we just found. It's the integral over all space, then we have this piece from the second excited state to m omega over h bar x squared minus 1. And both of those just have the exponent thing, and they'll just add up like that. Okay, and so actually doing that integral then, we do have to, I'm going to actually split it up into a couple different integrals as per the usual. We got this thing, 2 pi h bar. We got this 2m omega over h bar. We got this integral of x squared times the big important exponent dx, and then we also have the minus no prefactor, just the integral of the exponent, x squared dx. Fantastic. And that is from negative infinity to positive infinity. And I'm going to use the familiar results of a couple of different table integrals, those being from minus infinity to infinity, e to the ax squared. A is just some arbitrary constant. Doesn't have to do anything with the problem. This is just a mathematical fact that this Gaussian integral gives root pi over a, right? And then similarly, if you do the integral over all space of x squared times this junk, then you get 1/2 times the square root of pi over a cubed, right? So I'm going to use that here. We got this radical out front that hasn't changed yet. We got this 2m omega over h bar here. That integral is this integral, so it's 1/2 square root pi over a cubed. So a in this case is m omega over h bar. So we have h bar cubed over m cubed omega cubed. Hey, Gimli. And then we have the other integral, which is minus just pi over a, so root pi times h over m omega, right there. I'm going to factor through the radical on the outside, so that we get just m omega, or actually I'll leave the root 2 out front. Okay, 2m omega over h bar, and this 2 cancels out this 2. Get pi cancellation, you'll get an h bar cancellation, and m omega cancellation. So this is just actually now h bar over m omega, and this is 1. So we have 1 over root 2. Again, the m omegas cancel out, and the h bar cancels out, so you have 1 minus 1. So it's 0. So by doing that, we proved the orthogonality condition for the ground states to the second excited state. So we are good.